Okay, yes. All right, very good. Okay, so let's continue what we started last week, talking about unit structures. So I showed you how to count electrons, draw the unit structure. Some elements can expand the octet by using d orbitals, that's called hypervalence. And on the other hand, some other elements don't need to fill up the octet, and that's called hypovalence. And those are elements from group 13. Okay, so our goal today is to take a look at polarity of covalent bonds and take a look at formal charge as well. Okay. Okay, so let's take a look at polarity of covalent bonding. So first concept that we need to introduce here is electronegativity. Okay. So the electrons are usually not equally shared in a covalent bond, and electronegativity is a measure of the tendency of an atom to attract a bonding pair of electrons. And here, what we have here is a periodic table, and the number below the symbol of the element are the Pauli electronegativity for each atom. Okay? So it's a random scale. So the most electronegative element is fluorine, right here at the top, and the least go all the way in the diagonal, cesium and France. Okay, so cesium is too large, cannot attract anyone. On the other hand, fluorine is very small, very attractive. And remember here the order: fluorine, oxygen, nitrogen, fluorine, bromine, iodine, sulfur, carbon, phosphorus, and hydrogen. Most, least electronegative. Okay? All right. So with that being said, now let's talk about polarity. First concept here is polar and non-polar bonds, and then we will move on to polar and non-polar compounds. When analyzing the polarity of a bond, we're just going to look at the bond. Okay? So for example, CO2, you have here a bond between carbon and oxygen, and we are going to just take a look at the bond to determine if the bond is polar or non-polar. Electronegativity of oxygen is higher than the carbon, therefore we are going to have a dipole moment pointing from the least to the most electronegative atom, and that's going to be blue. To symbolize that we have a higher electron density in the oxygen, we're going to use delta minus, and on the other side, delta plus. Okay, so therefore, the bond carbon-oxygen is a polarized bond because of the electronegativity difference between carbon and oxygen.
Is that mu?
Yes, yes. That's the dipole moment. Okay, so that's how you look at the bonds. Just look at the atoms involved in the bond. However, when we talk about the polarity of the compound, we're going to look at the compound as a whole. And the molecular geometry will have a very high influence. For example, CO2. We're going to look on Wednesday. This is a linear compound. Therefore, this oxygen pulls to the right. The other oxygen pulls with the same intensity to the left, which means the resulting dipole moment is zero. Okay? So therefore, the whole compound is non-polar. And that's the biggest difference when you look at the whole compound and just at the bonds.
So the dipole moment for just the bond is mu, and for a whole compound, it's mu with a subscript R.
Yes, yes,
For a
that's the
compound.
resulting dipole moment.
Okay.
We're going to do the vector addition. All right, and then remember that polar compounds will solve polar compounds and non-polar compounds solve non-polar compounds. All right. So another way to determine if a compound is polar or non-polar is to use the electronegativity difference between the atoms. Okay? So we have here covalent bonds, ionic bonds, and everything in the middle. Higher the difference in electronegativity between the elements, higher the ionic character of the bond. And here there is a sort of a scale. If the electronegativity difference is lower than 0.5 between the atoms, that's a nonpolar covalent compound or bond. In between 0.5 and 1.6, that's going to use polar covalent compounds or bonds. And higher than 2, that's going to be classified as ionic bonds or compounds. Yes.
I have a question about just ionic compounds. Can an ionic compound ever really be non-polar since the difference in electronegativity is so great?
No. No, because the main characteristic of the ionic bond is a cation and an anion, right?
Okay.
So just the fact that you have these two species, you have a polar bond all the time. It can be more or less polar.
But never non.
No, never, never. Yeah. Okay, very good. Okay, so again, here we have the Pauli electronegativity values. So if we look for example, at the bond between carbon and hydrogen, and determine the difference in electronegativity. So you're going to see that carbon is 2.5, hydrogen is 2.1. So the difference here is 0.4. Okay? So see here that the difference is not zero, but it falls in the range for non-polar bonds. And that's how you would use those values here to figure out which range are you at.
Are
Yes,
you doing it carbon first because it's the first one that molecule?
it's always the
Absolute value?
absolute value, yes.
So hydrogen does not have the smallest electronegativity value. So how is it the least electronegative?
The least,
Yeah,
the least would be right here.
well, there was that scale with fluorine, oxygen, nitrogen, chlorine,
Bromine,
iodide,
sulfur,
carbon,
phosphorus.
phosphorus, and hydrogen.
Yes. Yes, so let me stop you right now. So that range are the elements that will do covalent bonding. Okay, so that's why we never showed you, okay, cesium actually is the lowest one, because cesium is going to be likely to be an ionic bond. Okay, so we chop at the hydrogen because those are the elements doing most of the covalent bonding. Okay? Good?
Yeah, and so all the elements that are not those, you just don't find them being covalent. Like I know that a lot of the copper and stuff, they're the ligands and stuff like that, which are kind of ionic. So we just don't find them as covalent.
So that's the thing. I don't want you to think that I'm giving you a soft answer.
Yeah.
But what we have is a scale between covalent and ionic. And most of the compounds will fall in between. So what you have are compounds that are very close to 100% covalent, and compounds that are very close to 100% ionic. Okay? So when you determine the difference between the electronegativities, you're going to localize them in the scale. So for example, the transition metals, depending on the case, the bonding is going to be more ionic or more covalent. Exactly, because depends on the metal, depends on the charge of the metal and what's around the metal. Okay? Okay. So very good. Now let's talk about formal charge. We are going to use the concept of formal charge to decide which Lewis structure for a covalent compound is the most stable. Therefore, the formal charge gives us an idea of how the electrons are shared in the calculation of the formal charge. The atoms are considered to have the same electronegativity. Ideally, in covalent bonds, electrons are equally shared between the atoms. Thus, we will look for formal charges equals to 0 as a sign of stability. Okay? So therefore, the rules are the most stable structure has the formal charge 0 for each atom. That means all the electrons are being perfectly shared and everybody has a slice of the pie. Double or triple formal charges on one or more atoms are not stable. And if there is a negative formal charge, it has to be located in the most electronegative atom. Okay, yes.
Is this the formal charge, is this to find it for both elements, you're gonna do it twice for whatever, or is it for the whole compound?
For each element.
Okay.
Okay. So we have to determine for each element. So how to calculate the formal charge? Very, very simple formula. We are going to start with the valence electrons for a given element, subtract half of the bonding electrons, and subtract all the lone pairs in that element. Okay, so we're going to do here the PCl3 as an example to refresh memory. Okay, for the PCl3, the newest structure is this one. So what we are going to do with the formal charge is to determine the formal charge for each atom and using the rule here, figure out if that structure is stable or not. Okay, so let's start with phosphorus. So formal charge for phosphorus. Number of valence electrons is 5 minus half of the bonding electrons. Each bond will have 2 electrons, okay? So each bond will have 2 electrons. 2, 4, 6 minus the number of non-bonding electrons. Right here at the top, we have 2. Five minus 3 is 2, minus 2 is 0. And we are going to represent the formal charge in between parentheses right here. Okay, so attention here with the number of bonding electrons. Each trace needs 2 electrons. So therefore, if you have a single bond, that's 2, double bond is 4, and triple bond that will be 6. And we are going to do the same thing for the chlorine. Valence electrons is 7 minus half of the bonding electrons. So attention now, we are just looking at one chlorine. Okay? So therefore, it's only one single bond. That's 2 minus 2 or 6 non-bonding electrons. Therefore, the formal charge for chlorine is 0 as well. So if you look at the second chlorine in the structure, it's the same as the first. There is one single bond and 3 lone pairs. Don't lose time calculating the formal charge. It's going to be 0 and 0 up here as well. Okay? So therefore, in that specific Lewis structure, we have all the formal charges 0. Therefore, this is a stable compound. And that's how I know that they have to be connected using single bonds. And for example, this structure here is less likely to happen because it's not going to have a formal charge 0 for okay? So formal charge is the ultimate decision maker regarding a Lewis structure. We are always looking for formal charge 0. If we need a negative charge, it has to be located in the most electronegative atom.
Say that, phosphorus chloride.
A what?
Say that element.
The name of the compound? Phosphorus trichloride. Okay, so that's a good time to talk about the sulfate ion. Correct. Okay, so sulfate that has a lot of electrons, and our goal is to determine the most stable structure. Okay, so for that we are going to draw all the possibilities, and we are going to decide which structure is the most stable using the concept of formal charge. Always look for all of them 0. If it's not possible and we have a negative charge, that has to be located in the most electronegative atom. Okay, so sulfate has a total of 32 electrons. So the first possibility is the most simple one. All single bonds and 2 lone pairs in each atom of oxygen. So that's the first possibility. So let's figure out if that's likely or not likely to be the most stable one using the formal charge, okay? We are looking for formal charge 0 for everybody. So let's start with oxygen. Oxygen started with 6 electrons. It's only making a single bond, so therefore 2 bonding electrons, and has 6 non-bonding electrons. So therefore, the formal charge for each oxygen in this case is going to be -1. It's not ideal. However, oxygen is very electronegative, so it's possible. Let's look at the sulfur. Formal charge for sulfur started with 6 electrons. There are 4 single bonds, therefore 8 non-bonding electrons and non-bonding electrons. So therefore 6 minus 4, that's a +2 formal charge. So we fell in the case of a double formal charge. That's by itself unlikely to happen. This structure is not the most stable one. Okay? Just the fact that we have a +2 formal charge that drags the stability down for that structure. Okay, so somehow we have to fix this structure. So the next possibility, we can move one lone pair of the oxygen to make here a double bond. Let's see what happens here. Okay, very good. So now notice that we have 2 kinds of oxygen in the structure, one making a double bond and one making a single bond. For the single bond one, we don't need to calculate anything because it's going to be the same. So we know that this one is -1. Let's take a look at the double bond. 6 minus. Now we have 2 covalent bonds, therefore 4 bonding electrons and 4 non-bonding electrons. So that's going to yield a formal charge equals to 0. Okay. So that extra double bond increased the formal charge for oxygen and moved to 0. So that's a positive development. Let's take a look at the sulfur. Six minus 1, 2, 3, 4, 5 covalent bonds, for 10 bonding electrons, and no lone pairs. 6 minus 5, that's a +1 charge. Is it better than the first version? It's better. So that means the second structure is more likely to exist than the first. So let's do one more thing here. let's add one more double bond and see where we end up. Okay. So for oxygen making a double bond with two non-bonding electrons, the thermal charge is always going to be 0. Oxygen single bonding is -1. Now let's take a look at the sulfur. Six minus 1, 2, 3, 4, 5, 6. So that's 12 minus 0. That is 0. So we have more zeros than the second case. We have two negative charges. They are located in the most electronegative element in the bond. So that's allowed. And here's the trick. If you add up all the formal charges, you have to get the charge of the ion outside. Okay? Okay, so therefore, the third structure is the most stable among the three. So let's do here one thing, just to see what happens. Okay? So now let's add one more double bond and see what happens with the charges. Okay? You can draw anything you want, right? So there are things that are more stable and less stable. So 3 double bonds and 1 single bond. Let's see how likely is this to happen. Okay, oxygen double bonding is always 0. Oxygen single bonding is -1. The charge outside is 2 minus. We have -1, so therefore sulfur has to be -1. How likely is sulfur to get a -1 charge bonded to oxygen? No, that's not likely. Okay, so therefore, the structure with 3 double bonds and 1 single bond is less likely to exist than the third one. Okay? So with that, among the 4 structures, the most likely to happen is the third structure. That's where we have the best thermal charges. It doesn't mean the other structures do not exist. They do exist, but the percentage for each is going to be very small.
Is there a reason why you do that 1/2 of all the electrons with their pairs rather than just counting the number of?
Yes, absolutely. Because when you have the covalent bonding,
Yeah.
you are sharing the electrons, right?
Right.
So a bond has to be has to have 2 electrons.
Right.
If you are sharing them, you just get half.
I understand that, but you're always saying half twice. Like I can just count the electrons that are. I mean, I just wonder if there's like 1/2 times 4 is always 2, 1/2 times 10 is always 5. Like if I just count the number of.
Yeah, you just count the number of bonds. Yes.
I was
Yes.
just wondering if there's a reason coming down the line that You do the 1/2.
It's just what the book, the book shows, but doesn't matter, it's the number of phones that you have. Yes,
Yeah.
it doesn't matter. So that's how I know that Xenon F4 is only connected with single bonds.
What they know about.
The Xenon F4,
Oh,
the Xenon F4, that's how I know that we only have single bonds. Because I did the thermal charges and all of them are zero. But you can play and add double bonds and see what happens. It has to destabilize this structure. Okay? All right, any other questions regarding thermal charges? Okay, so the next homework is going to be a very long one. I will ask you to draw a lot of Lewis structures and calculate all the thermal charges. However, you can think about one thing. Oxygen making single bond is always going to be 1-, doesn't matter. Okay? So, and double bond is always 0. So that helps you to go a little faster. Yes.
So do you not have to write out like the 6- every time? Like the calculation for formal charge for each of the atoms?
Yeah, just the number is more than enough. Yeah. Any other questions? I think then today is a good point to stop. We will resume on Wednesday.